So we have just a few more examples from section 6, and then we're going to wrap it up. So Anna walks 90 meters due east and then 50 meters due north. What is her displacement from her starting point? So again, draw a picture, and it's helpful to know what the directions are that you wrote down. So just like on the last problem, here's north, here's east, just reference. Now, Anna is starting at wherever she is. She's going to walk 90 meters due east. And then she's going to walk 50 meters due north. Now that's going to make a right angle there. What is her displacement from her starting point? So from her starting point to her ending point is this right here. We want to know that distance. So what have I just created?
Hypotenuse.
A hypotenuse of a right triangle. That's right. Now the displacement is a length, right? So we can call that D right there. The displacement of Anna, we could put a subscript on there if we needed to. So D sub A would be perfectly fine. I'm just trying to get you guys used to notation. So when you're doing a problem, how should I label something? You know, stuff like that. So here you go. Now, how would I find this? What would I do?
A squared plus b squared equals c squared.
Pythagorean theorem, right?
Yeah.
And I don't want to go a squared plus b squared equals c squared because I already know that like in my mind. So I'm going to go straight to d sub a, which I know is the hypotenuse, equals, and I know that a squared plus b squared equals c squared. I know I need to square root both sides to get to just what c would be, right? Which I know is d sub a. So I'm going to go straight to the square root of, and the two sides added together after I square them. So I have 90 meters squared plus 50 meters squared. Okay? And then I'm on my calculator, typing that in.
I got 102.956.
Okay?
Oh, that's like the actual one. Those two combined in the square root is 10,600.
Well, you can give me the,
Oh, okay.
you know, because I'm typing that straight into my calculator like that,
Yeah,
right?
I got
102.956.
Okay, 102.596.
Yeah.
And that's going to be meters. 956?
Yeah, 956.
Okay, sorry. 956. All right, now go back to the problem and I look at my significant figures and I figure out that I can keep how many significant digits?
2.
Actually, it looks more like 1 because I'm not sure about that 0 on the 90 and the 0 on the. So I'm keeping 1 here.
So it'd be 100.
So we're going to say 100. This is actually 100 meters. Okay, now, what about the angle?
What do we do, like, so we already, a triangle is total 180, so we got 90 already, so we have another 90 to do stuff with.
So we could do
Which angle on this triangle am I trying to find?
the opposite of 50.
This one here, right?
Uh-huh.
Okay, so I can call this my angle theta.
Oh wait, that's
Now, which sides of this triangle would I use to find my angle theta?
the adjacent.
Yeah.
The two that I knew to begin with. I would not use the one that I just calculated because if I use that one and I was wrong in the first place, then I'm definitely wrong in my answer here, right? So I'm going to use my opposite and my adjacent. So what trig?
TOA. So toe.
So that's which one?
Tangent.
That's tangent.
There.
So we're going to set up tangent theta, which we don't know, right? Equals the opposite, which is 50 meters, divided by the adjacent, which is 90 meters. Now what happens here is a couple of things. The meters divide out, which is good. Otherwise I wouldn't be able to do this.
The zeros.
Also the zeros, so the 50 90ths reduces to just 5/9. So when I do this in my calculator, I don't have to type in 50 over 90, which is nice.
29.
Now, we're going to use inverse tangent to get theta by itself here. So I wind up with theta equals
29.
tangent inverse 5/9, When you type this into your calculator, you're going to want to make sure that you are in degree mode, not radian mode. So in your calculator, it should say DEG somewhere.
Yep, top right corner.
Okay, and then what do you get?
29.0546.
29.0 something something something, right?
0546.
Okay, so we got all these amazing digits here.
Did I do one wrong?
How many digits can we keep?
1.
So what's our answer going to be?
30.
Yeah, we're going to say 30. So this is roughly, not equals, but roughly, right? So we're rounding
Yeah.
30 degrees.
How'd I get that though? Well, actually,
So now it's 30 degrees, and we have to specify the direction. 30 degrees what? So she initially was traveling east, and then she turned north. So what we're going to do is we're going to say 30 degrees
northeast.
north of east. It's not northeast, it's north of east. Okay, so we have 100 meters here and 30 degrees north of east here. So our final answer is 100 meters, 30 degrees north of east. There you go.
So after the displacement, you have to do both the.
Yeah, displacement is a vector. So it's magnitude and direction. So you have to have both. Okay?
Vector.
All right, so now velocity vectors. So we had displacement vectors, which is like more like a position. Now we have velocity, which is position over time, right? So displacement over time. So now, what do? Describe the object's speed and direction. How fast are you going? And which way are you going? The velocity vector, again, with the arrows, this is supposed to be an arrow here. And for whatever reason, they just don't print. So if I ever don't mention it, just remember that that's supposed to be an arrow. Points in the object's direction of motion, and the magnitude is the object's speed. So we have a speed, the magnitude is the speed, and then the direction is which way you're going. Okay? The motion diagram for a car starting from rest. So the displacement vectors are lengthening, which means the car is speeding up in whatever direction it's going. And we've seen enough diagrams now that show the dots. We know that these are equal intervals of time here, so we know that the car is speeding up. The displacement vector and the velocity vector, notice the similarity here. The longer the velocity vectors indicate the car is speeding up. Okay? Good there?
Yeah.
All right. So then, the ball's motion diagram. Jake hits a ball at a 60-degree angle from the horizontal. It is caught by Jim, so that means it went up and then it came down. Draw a motion diagram of the ball that shows the velocity vectors rather than displacement vectors. All right, I'm going to give you a little bit of time to try that on your own, and then we'll come back and talk about it. Go ahead. So there's a few things we got to think about here. How is the ball hit? 60-degree angle is pretty steep.
Yeah.
2, we just saw, let me scroll back here, we just saw this velocity vector diagram here. Now when the ball is first hit, we also have to think about the motion of what that's going to look like. So we come back to this. So the motion is going to look, kind of like that, right? All right, so our diagram is probably going to look kind of like that. All right. Now we've also seen some diagrams where the velocity or the motion in the horizontal direction is different than the velocity or the motion in the vertical direction. Okay? We've separated those two things out before. We've seen that a couple of times. So we're probably going to need to do that too. All right, so let me get rid of this. Now, in addition to that, I've also been giving you guys this notion that we need to have a coordinate system. So positive x will be to the right and positive y will be up. So that's the first move. Now, the next thing I want to do is set an origin. How come I want to set an origin?
So we can show the 60 degrees.
So I can show where the ball started. I can show the 60-degree angle that we have to begin with. Lots of reasons to put that origin down, okay? Mostly so that I can have a beginning place. Now, it says Jake hits the ball. So I'm going to put Jake over here. And then Jim over here catching the ball. Now, I also want to represent equal intervals of time. Okay? On our motion diagrams, we always have equal intervals of time. So let's see. I can put there, 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 there. And here's Jim. Okay, so there's equal intervals of time. So now what's going to happen? Well, the first thing that's going to happen is the ball is going to go up at a 60-degree angle, right? So from Jake hitting the ball up at a 60-degree angle, let's say that's a 60-degree angle, and the ball is going to be right there after my first interval of time, so I'm going to call that 60 degrees. Whether that's actually 60 degrees or not, I don't know, but I made it look like 60 degrees, and then I called it 60 degrees. Okay? So that's my first interval of time. Now, I know if I throw a ball straight up into the air, that it will start slowing down immediately and eventually come to a stop, and then it will start to come back down, right? And as it comes down, it's going to start speeding up. I also know from things that we've talked about in class that if I throw a ball horizontally, it's never going to slow down horizontally, okay? And if I put those two things together, then over equal intervals of time, that ball is going to be equally spaced as we go across horizontally, but slowing down vertically until it gets to its highest point. So that means this distance from here to here has to be less from here to its next elevation on the next interval, okay? So let me get rid of these marks so that I'm not confusing myself. Okay, and whatever this distance was from the first one to my dot, I have to make it less to my next dot. Okay, so here we are. So it's got to come down a little bit. And then the angle's got to be a little bit less. And then the angle's got to be a little bit less. Okay, and I probably am not decreasing it quite enough. The angle's got to be a little bit less. Okay, now the angle's got to be like flat, and then I got to start coming down, and then I got to start, yeah, see, I'm not coming down fast enough, right? But that's fine, I can just extend my axis. So let's see, more equal intervals. So I'll just move Jim, that's fine. So now I'm coming down a little bit faster, and my equal intervals are not equal enough. Coming down a little bit faster. And now maybe, where am I? Here. Okay, so Jim's actually over here. There we go. And that's fine. That's the idea.
Wait a second.
Okay? You see how that works? The main idea is that when we have this vector going on, there is something called components that I can draw. Every single time there is a horizontal displacement, and each one of these is equal. Okay? So here's the ball, here's the ball. Every single one of these horizontal components of the displacement is exactly the same. The ball is always moving horizontally the exact same amount. Okay? Vertically, that's not the case. Vertically, this ball moved that much, and then it 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 barely moved up at all, and then it didn't move up at all, and now it's coming down actually, and now it's coming down more, and then it's coming down more, okay? If I just look at the vertical. But horizontally, it's moving the same amount each time. You see how that's different as it moves up and down?
Yeah.
Okay, so that's kind of the goal of what we're doing We're not talking about two-dimensional motion in this chapter. This problem, though, is trying to get us to think about what two-dimensional motion looks like. Because in the next chapter, we're going to be talking about two-dimensional motion. Okay? Got it?
Yeah.
All right. So that's how you do that one. Now, the last problem. P and Q are two vectors of equal length but in different directions. So we have P and Q sitting over here. Which vector shows the sum of P and Q?
B.
Think so?
Yeah.
Wait, no.
Yeah, because they're both like that. So goes that way.
If they're like that, wouldn't it be this one?
The arrow. See the arrows?
It'd be like this one. Oh, the sum of P and Q. Ah, okay.
Okay, so it's like that. So it's
How do we do the sum of two vectors?
B.
Connect them.
Tip to tail, right?
Uh-huh.
So we would take Q, this vector, and put it on the end of P. And then the result starts here and goes to the end of the other one. So it has to be B. All right? The other thing you could do is you could say, well, I went to the left first, and then I went up. Where did I end up? From here to there. I had to go left and I had to go up. The only one that goes left and up is B. So that's it. That's like the introduction to vectors, displacement, and velocity in this chapter. So we're done.
Alright, let's do some homework.